Oh, it's time to get real with the first derivative test. Very, very exciting. Let's see what it's all about. So basically, we're going to come up with some conclusions. The first derivative test says one of two things. If f prime of x changes from positive to negative at some x value, there is well, let's take a look at this. And I want you to copy this with me, this idea. F prime's positive means we've got a positive slope, and then it goes negative. Oh, what happens at the point where we go from a positive slope to a negative slope, you say? We get a relative maximum, right? Positive slope, negative slope. And I'll draw that out. So we go from increasing on f, another way of looking at that, to decreasing on f. You're going to have a relative maximum. That's it. And honestly, I think one of the best ways to understand this is just by doing out those hand motions. Don't memorize it, feel it. So relative or local maximum. Nice. And that could take the shape of where the derivative is 0 or at a point where the derivative is non-existent. What about the opposite? Meaning if f prime changes from negative to positive at x equals c, there is well, let's think about this. From negative to positive. All right, let's do that out. A relative minimum. From left to right, if we change from negative slope to positive slope, we're going to have a relative minimum. And that could also happen where we have a place where the derivative is not defined, where it doesn't exist. Okay, let's take a look at that. So that would be a relative or local minimum. That's it. So now in the rest of this video, what we're going to do is we're going to go over two problems that allow us to find where all of the local minima and maxima, all of the valleys and hills are on a graph without using a graphing calculator. It's pretty sweet. Let's do this. All right, that's it. That's the first derivative test. So use the first derivative test to find all local maxima and minima on the following function. Justify your answer. So justifying your answer means I'm going to be a little more formal than just using a sign chart. I'm going to do this as if you're taking the AB or BC exam. Some of your professors and teachers will allow you to just use the sign chart, so you can skip over the part where I write out the wording. I'll do that last. Okay, two problems. First one here. So I got to find the derivative because that tells me about the behavior of f, where we're going up and down and vice versa on f is what we're interested in. So we'll find the derivative. F prime of x is equal to 6x squared minus 6x minus 1 turns into 0. Now from here, I need to find my critical numbers because the only place where a relative minimum or maximum can happen is where the derivative is 0, right? Nice and smooth, or undefined. We saw that in that last picture right there. The derivative is 0, derivative's non-existent. Derivative 0, derivative's non-existent. Those are the only two places to look. So we're looking for our critical numbers. So I set that equal to 0. It's never going to be a non-existent because that's a polynomial. There's no value that makes this function, no x value that makes this function undefined or non-existent. So I'm going to factor out a GCF, 6x times x minus 1. Funny how these work out so well. And now we've got x equals 0 and x equals 1. These are the places where we could have relative maxes and mins. I'm going to draw out my sign chart. That's what it's often referred to. It's just a number line with markings at your critical numbers, 0 and 1. Just like we did for where we're increasing and decreasing. That's essentially what we're doing here, is doing the same thing we did in video 1 in this lesson. I like to mark this as f prime so I know what it is I'm looking at. And so now I'm going to do test points. I'm going to plug 0, well not 0, but a number less than 0 into this. So in my head, I plug in, let's do negative 10. And that'll be negative 10 minus 1. Now all I'm doing is checking the signs. So that's negative, and a negative times a negative is a positive. So we'll be positive on this interval. That means that f, if you really want to, write it right there, is increasing. Okay, now let's keep going. I'm going to plug in a number between 0 and 1. That's going to be 1/2. Now normally that's gross to plug in, but all I'm checking for are the values of the signs of the derivative. And as always, I usually plug these numbers into factored form. I think it's easier. This would be positive, that would be negative, and a positive times a negative is a negative number. So I'm going to take that 1/2 out of there. That's getting all up in my business, and I don't want it there. So it's going to be minus. Now we plug in a number to the right of 1. Okay, so we'll do 6 times, how about 45,000? I literally plug in numbers like that sometimes. Why not? So you have 45,000, and you're not writing out this work unless your teacher wants you to show it. You could do it mentally and say, well, that's positive times a positive is a positive. On the AP exam, you don't have to show any of that. They trust that you know how to plug numbers into a function. So we're decreasing on f here because our slopes are negative. We're increasing on f here because our slopes are positive. So let's think about this. The curve goes from increasing to decreasing and then decreasing to increasing. Boom. We've got a relative maximum at x equals 0 and a relative minimum at x equals 1. Now, this is not justification enough on a major AB or BC exam, but it is justification enough for a lot of teachers and professors. So you just want to see what it is that your teacher or professor expects from you. Now, I'm going to go over that formal part. What I like to state is, I state first my reasoning. So I'll say f has a relative or a local maximum where f prime changes from positive to negative. That's it. And I'll abbreviate that from, don't abbreviate on a major exam though, that's a major problem. Positive to negative, which occurs at x equals, well, where do we go from positive to negative? 0. Now, we were asked for the local maximum, right? So that means that we actually need the y value. So what I'm going to have to do is I'll find f of 0. And f of 0, when I plug it in, that's going to be negative 1. That gives me the point 0, negative 1. So I should erase this and say that occurs at 0, negative 1. You're not asked for just the x value, you're asked for the maximum. And then the same way, we could say f has a local minimum. So f has a local minimum at, and now, well, or at where, make it a little bit neater, f prime changes from negative to positive. This is being very formal. Changes from negative to positive, and this occurs at, and now we need the point. So the minimum is where f went from decreasing to increasing, or f prime went from negative to positive. So we need that at 1. And again, I want the y value, not the slope. That's why I'm plugging in here. So that's 2 times 1 cubed is 2, minus 3 times 1 squared is negative 1, minus 1 is negative 2. So that's at the point, let's see, 1, negative 2. That's it. That's how you formally do it. The next problem, and I'm not going to go over as formally, but keep in mind you needed your y value there because they asked for the local maximum and the local minimum. Let's go to the next one. All right. So even though it says justify your answer here, what I'm going to do here is I'm only going to do the sign chart now that you guys have seen how to justify it. Use the first derivative test to find all local maxima and minima on the following function. We're going to do much the same way. I wanted to do this one because it's one where, well, the derivative's a little interesting. Let's see. So we take the derivative, little chain rule here. That'll be 2/5 derivative of the outside times all that stuff to the negative 3/5 times the derivative of the inside. Nice. And now from here, what I'm going to do is I'm going to rewrite this in such a way that I don't have a negative exponent because I'm setting everything equal to 0. 2 times 2x is 4x all over x squared minus 9 to the 3/5. Beautiful, beautiful, I do say. That's a terrible accent, whatever it was supposed to be. Don't forget the 5 that goes down there. Now, this is non-existent when the derivative is, well, undefined. And that happens where x squared minus 9 equals 0, because we're going to get a 0 in the denominator. And that is when x equals plus or minus 3, solving that out. So you have two critical numbers at plus or minus 3. And we've got a critical number at x equals 0. Because if I set this equal to 0, that will occur when x is 0, 4x equals 0. And the denominator will equal 0 at plus or minus 3. Right? 3 squared or negative 3 squared gives you 9. All right, back to a sign chart. Same thing, no difference. I call that sign chart G prime. We have three critical numbers to check. Negative 3, 0, and 3. And we're going to do the signs. Now, the sign chart here, I'm going to use this, and I'm going to do this mentally. Let's explain it out loud, though. So I'm going to pick a number. X equals negative, I don't know, 10. Well, if I plug in negative 10 into this thing, and I square it, that's going to get me a very large positive number. Minus 9 is positive. All of it is positive. But this is negative, and a negative over a positive is a negative. So that means g is decreasing on that interval. All right, let's do it again. Between -3 and 0. Well, we've got -3 to 0. I'll pick like -1. We've got a negative number up here. -1 squared is 1 minus 9, negative. So the 3/5 is still negative. This is a negative over a negative is a positive. So we are increasing on g. From 0 to 3, we'll pick something like 1. Well, that's going to be positive. This 1 squared minus 9, negative. So the 3/5 still negative. So we've got a, well, let's see. We've got a positive over a negative. That's going to be a negative. So we're decreasing on that interval of g. And then, I don't know, 45 billion. 4 times 45 billion is positive. That squared is positive, minus 9, the whole thing is positive. So g is increasing there. All right, so now what does that mean? Well, we're decreasing from -∞ to -3. So we're going down and then up. So we've got a relative minimum at x equals -3. We're increasing to decreasing at 0, so we've got a maximum at x equals 0. And then we go decreasing on g to increasing, which means we have a minimum. Now, some very important pieces of information here. Though we were decreasing to increasing, at -3 we had a sharp turn. Right? We knew that because the derivative was not defined. And at this point too, at x equals 3, we also had a place where the derivative was non-existent. So we went decreasing to increasing. Very cool. All right, so what do we have? Well, we've got a minimum here, a maximum there, and a minimum there. Let's find those values. So g of -3. It's going to be something funky. -3 squared is 9. Actually, that's not bad. Minus 9 is 0. So the 2/5 equals 0. So you've got a min at the point -3, 0. G of 0, let's see what that equals. Well, 0 squared minus 9 is -9. So that's going to be -9 to the 2/5, or the 5th root of 81, right? -9 to the 2/5 would have been fine too. And so that's, yeah, a weird point. The 5th root of 81, sure. And then we've got, let's check this out. Well, 3 squared is 9 minus 9 is 0. So g of 3 is 0. And so you've got a min at 3, 0. That's all. So I'm not going to go over the formal justification this time. You had that in the first part of the video. It's a lengthy one, this video, but it goes over some of the most important stuff you're going to see in all, in my opinion, of Calc 1. See you in the next one.